in problems related to single phase induction motor. We stopped last class at this part, at that slide. So we will continue today the remainder of single phase and hopefully to start in the new topic of stepper motor. Here يا شباب the problem combined between the normal operation of single phase induction motor and also a problem regarding parameters identification of induction motor. You learned previously in E360 course the parameters identification or determination of three-phase induction motor يا شباب. We were determining the parameters using two different tests. One test is called short circuit test, blocked rotor test, and this blocked rotor test is equivalent to short circuit test of transformer. And the other test is called no load test, and it's equivalent to open circuit test of transformer. So these tests are equivalent for induction motor and transformer. Right, what is the aim of the tests? The aim is to identify the motor parameters. Right, let's see the problem, and we can recognize from the problem how we can make these tests and calculate the parameters based on some given data within the test. So the problem says here the following test data are obtained from 1/4 horsepower single phase induction motor. طبعا can you see يا شباب 1/4 this small power cannot be obtained for 3-phase, or يعني you can find it in 3-phase rarely, يعني very few amount of motors can be designed for such horsepower as 3-phase motors. Normally 3-phase motors are designed for high power. However, you can find few made يعني in this range of horsepower. يعني I could find already, I could found some of small rating motors 3-phase induction with this يعني or small maybe smaller horsepower made in India, okay, and I'm يعني made a purchasing order already to use it in our lab research. So it's possible to find it, but very few companies can produce very small 3-phase power. However, for single phase you can find it easily, such a small power rating here. So this is now the single phase induction motor rated. This is the output power now. Single phase 120 volts. So this is now considered as the input volt. طبعا it's يعني RMS value. Here we shouldn't say phase or line because this is single phase يا شباب. So here this is representing V1 RMS value. Frequency is 60 hertz. N is 1730. What is this N يا شباب? What is this speed here? Is it synchronous speed or rotor speed?
Rotor speed.
Rotor speed, exactly. We don't have synchronous speed with this value. So this is now representing the machine rated speed induction motor. Stator winding main resistance, which is R1, is given. So R1 of the motor is already given without the tests because it can be already measured using ohm meter. The same what we have made in parameter identifications of DC motors يا شباب. The armature resistance, we could measure the armature resistance by means of ohm meter. And the same here is for induction motor. Sometimes we use the form factor يا شباب. Form factor is the relation between RMS and average, or AC and DC quantity. Why? Because the value of R in AC quantity will be different a bit compared to the R in DC quantity. Why? Because the current in AC will flow in the outer surface of the conductor. However, the current in DC will flow in the central core of the conductor. You know, Shabab, this phenomena is called skin effect. For AC current, current moves at the surface of the conductor. طبعا with a certain depth within the conductor diameter. But in DC current, the current flow inside the conductor, exactly at the center of the core. Okay. For that, the resistance of AC may be different a bit compared to the DC one. So we multiply only by the value of I forgot the name of the factor. I just said it. تمام. we multiply by this factor. It's almost around 1.1 like that. Form factor. Form factor. Okay. So we multiply by the form factor. طيب. here nothing is given for the form factor, so we can consider that the AC resistance is equal to the DC resistance already obtained from the test. And also to be honest here, it's still that the stator winding resistance is, so it means this is now considered as the AC value of resistance. It means already this value may be obtained by multiplying form factor by the value of resistance obtained by ohm meter. Is it clear, شباب? What I discussed now is clear?
Yes.
So let me ask you a question now. How we can measure the resistance of three-phase induction motor? If I have three-phase induction motor, شباب, and it's start connected now, how we can obtain the winding resistance? So let me draw the windings like that. This is for three-phase induction motor. It's not related to our problem, but just this is to to make brainstorming with us. Now we have the three-phase winding like that. If I use ohm meter, I will use ohm meter like that. This is the ohm meter, okay? And I will connect the ohm meter between two phases like that. So what will be the value of R1? If I have here, assume this is R like that. What will be the value of R1?
The reading over 2.
Exactly. So the reading which will be obtained here, which will be R2, 2 by R, صح كده؟ the reading of ohm meter will be 2R. So you should divide the reading over 2, okay? But this will be the DC resistance. So the exact resistance for R1 in case of three-phase induction motor will be form factor multiplied by reading over 2. Is it clear? تمام يا شباب? Because the reading here will be the reading of ohm meter, which is nothing but DC value. Because the ohm meter يا شباب has internal battery, so it will give you the DC value of resistance. In order to give the AC value, and we said it's different because the current flow in AC at the surface of the conductor, so the value will be different a bit. So this is the way how we can use the form factor in order to obtain any resistance. So let me erase this part because it's not related to the problem now, and continue our discussion. So we obtained now we have now the value of R1. We have two different tests. One is called the blocked rotor test, and it's equivalent to the short circuit of transformer. For that, you will find that the voltage here is smaller than rated volt, because at short circuit we cannot apply the full volt because the current will be very high. And the current of blocked rotor should be around rated يا شباب, and it's referred to be at rated. So this is now representing the current of the motor at blocked rotor test, and this is the power measured due to blocked rotor test. So like transformer, we have three readings: voltmeter, ammeter, and wattmeter readings. And we should use these readings in order to obtain the motor parameters. Not only using blocked rotor test, but also using the no load test. No load test, it means we will supply the motor while there is no mechanical load. So in this test, شباب, the rated voltage will be applied, and we will measure the current at this no load. It will be around 3.5 like that, and power at no load as well by the same way, for the same measurement. You can see that here no load current is not small compared to maybe full load as we discussed. 3.5 out of 5, which means شباب, we have high no load losses of this type of motors. Okay, so we have now the two data of the two tests, and we need to obtain the motor parameters. This is the first thing, شباب. In order to understand that, let's apply firstly at standstill. At standstill means motor is not moving, and S equals unity. If you apply this to the equivalent circuit, you remember the equivalent circuit, we discussed it last class. This is our equivalent circuit. So if you apply S equal 1, you have here S and you have there S. Apply S equals 1 here, you will find this value will be 0.5 R2 prime, and this value will be 0.5 R2 prime over 1. So it's also 0.5 R2 prime. Now let's compare يا شباب between this branch and this branch, between the values of x2 prime plus 0.5 r2 prime with the value of x magnetization. Which one is higher يا شباب? The branch of rotor or the magnetization branch? Which one has higher impedance?
The magnetization.
Magnetization has higher impedance. This is right, which means the current that will flow here will be relatively small compared to the current that will move in this branch. For that, we can neglect the current in the magnetization branch and remove this branch from the circuit if the motor is working at standstill. So this is now representing يا شباب the equivalent circuit at blocked rotor test. Why? Because the motor is not moving. S equals unity. In this case, you have the applied voltage, you have the current and the power consumed by the circuit. So now, regarding the resistance, you have R1, 0.5 R2, 0.5 R2, so it's R1 plus R2. And you have I and P, so you can easily obtain the value of R2 because you already have R1. So we can say now R1 equals 2.9 ohms, it's a given, and B blocked is nothing but I blocked square multiplied by total resistance. So from here, we can obtain the value of R2 prime. So this is now the value of R2 prime. Is it clear? Any question, Shabab, regarding this calculation? Right, good. Now, we could obtain the real part of the impedance. We need to obtain the imaginary part, which is x1 and 0.5 x2 prime and 0.5 x2 prime, so it's x2 prime. So the total impedance now, sorry, total reactance now will be x1 plus x2. Now, Shabab, we have VI and P. We already obtained the real parts, and we can obtain the imaginary part if we obtain the complex number value, the absolute value. So simply, if you just divide V over I, it will give you the impedance value, which is the absolute value of the vector. So we can say now Z blocked rotor equals 43 volts over 5 amperes, which is 8.66 ohms. This is now considered as the absolute value of the impedance, which can be equal to square root of 2 R2 prime plus X2 prime. Sorry, R2 square plus X2 square, which is the real part of the impedance and the imaginary part. We already obtained the real part. Fadal?
The Z blocked rotor, the Z blocked, it is by a DC source?
No, no,
DC
no,
voltage
no.
and current?
لا, this is AC. All of these tests are AC يا شباب.
Okay.
يعني multiply 43 by 5. What will be the value?
It is around 215.
43 by ثواني كم حسبتها تبع كم 43 by 5 يعني 40 by 5 equals 200 صح and 3 by 5 equals 15 so 215 is it right صح يا شباب طيب in AC power equals VI times power factor so the value of B here is different to VI so it's AC test not DC test is it right يعني if it is made using DC test you will find that V by I equals power and here it's not the same because it's AC now ماشي so no load and blocked rotor tests شباب are AC tests it's not DC tests for that when you divide يعني V over I it will give you the amount of Z طبعا if it is DC again تفضل
this means no load and blocked rotor. It's only for the AC. It's not can be for DC.
Exactly. يعني when we make the parameter determination for DC motor, did we use blocked rotor and no load test? We used different tests, صح? يعني we did not use that. Yeah. But we used this test for transformer. صح? Which is AC machine as well. We use it for induction motor. We can use it for synchronous motor and so on.
I get confused, Doctor, between no load test and no load speed.
لا don't worry, ما فيش مشكلة. يعني no load speed means the motor is working, okay, without load, and it's working at the highest speed. This is no load test made for DC motor, you mean? Is it right?
Yes.
تمام. يعني it's equivalent here. يعني no load here, it's equivalent to what we made for DCA motor. But يعني in DC motor we did not make blocked rotor test in order to obtain the parameters. يعني in DC motor we made acceleration test, we made time constant test. يعني we made many tests in order to obtain the motor parameters. But here for AC machines we need only 2 different tests besides getting the resistance using ohmmeter. Okay, these tests are equivalent short circuit or blocked rotor or يعني no load or open circuit tests. Fine. So again يا شباب, we can calculate the impedance by just dividing V over I. This will give you the amount of impedance. And once you already have the impedance and real part, you can easily obtain the imaginary part. So for now, we got the imaginary part, which is 6.53 ohms. And most of times, the impedance of rotor and stator are equal. So, the reactances of stator and rotor are equal. So we can assume that x1 equals x2 prime equals the amount of reactances obtained over 2. So this now represents x1 or x2 prime. So from blocked rotor test, we could obtain the value of R2 and X2 طبعا beside the value of X1 already. And we could obtain. Fine. We still have some unknown parameters for the motor. If we return back to the equivalent circuit again, we're still missing the part of XM or XMAG. We need to obtain it. How we can obtain it? From the no load test. In no load test, the motor is working at no load, which means the speed is very high. Okay, the speed is very high, and S will be very small. If you substitute in the values of S in the equivalent circuit here we have R2 prime over S. If S is very small, so this value will be very large. Is it right?
Yes.
So in this case, we can neglect the current moving in this branch and consider only the current moving in that branch. So one of the XM parts will exist in the circuit now. However, if you apply S here as very small value, almost the value here will be 2. So this will be R2 prime over 4, which means we still have XM higher than this branch. So we can remove this branch from the circuit. So now the equivalent circuit for no load test can be this branch in the down for the backward component and that branch in the upper for the forward component. So this is now شباب the equivalent circuit at no load. Do you find any difference between this circuit we plotted now and the equivalent circuit of the motor? Is there any difference, شباب? يعني we assume that the branch here will not exist and the branch here will not exist. يعني we remove one branch from here and one branch from here. Is there any extra component now?
No.
But what about this element?
Yes.
We have here R rotational. Actually, we do not have R rotational in the equivalent circuit. However, in power calculation, and now the motor is working at no load, what are the different power losses exist with the circuit? We have few copper loss because the current is small, relatively small compared to full load. We should have core loss. Because of that, we will have the magnetization sorry, we should have RC in parallel here, but it's not included. And we have also friction loss. For that, Shabab, in blocked rotor or no load test, we have to assume another parameter in order to consider the different losses exist in the circuit. So for the no load test, we have already some core and friction loss. So we are assuming now a series resistance of R rotational, which will considered as a representer for the losses of no load or rotational loss, which is a combination between core and the friction loss. So now, for the no load test, we can calculate two things: the value of Xm, which is missed now, and also the rotational loss of the motor. طبعا, how many resistances we have here in the circuits? We have here R1, we have part of R2 prime, and the resistance which will represent the rotational loss. So now, after measuring the no load losses here, we can say that I no load multiplied by summation of resistances, طبعا I no load square, multiplied by the summation of resistances equals the power of no load. So easily we can say, I don't know why the relation is not given, maybe the reference here calculated in different way. This is our assumption we have made here. The resistance R2 prime over S. Yeah, this is also we said all of these parts. It's a try to assuming why we have R mechanical here or R rotational. But in terms of relations, he didn't obtain it here. Yeah, the relation is here. We can say now B no load equals I square multiplied by R1 multiplied by R rotational multiplied by 0.5 R2. So this is now the total losses, and we have B no load and I no load as well. So we can obtain the value of R no load, and we had R1 and R2 prime before, so we can get rotational resistance, and from rotational resistance we can get the value of rotational loss, which is I square multiplied by R rotational. So finally we can say power rotational equals I no load square multiplied by R rotational, which is 3.5 square multiplied by the value of 10.2 ohms. So this will be the value of rotational loss of this motor. Then we will have the value of طبعا this equivalent circuit is not for no load. This part is will be used for part B, okay? Or not for part B even. This is the overall equivalent circuit, maybe for part C. We will see this later. We're still working with the no load impedance here, or no load circuit here. So we would like now to obtain the value of X mag. Simply, we have impedance, we have volt and current. So we can say now Z no load equals V no load over I no load. And after getting the value of Z, we know the real part of the impedance, so we can obtain the imaginary part. As same as the other previous test. So finally, Z no load equals R no load square plus the imaginary parts 0.5 X mag plus X1 plus 0.5 X2 prime. And we have these two values previously determined here, so we can calculate the value of X mag. And finally, this will be the value of magnetization reactance. Now, Shabab, after obtaining all of parameters, we can substitute in the equivalent circuit by all of the A parameters here. So this is now representing the motor equivalent circuit with the exact parameters, or not exact, we can say with the determined parameters from the two different tests. Any questions, Shabab, regarding the no load test and the blocked rotor test? Is it clear?
Sorry, Doctor.
تفضل.
The R no load, is it the same as R rotational?
R no load here means the total resistance of the circuit during no load test, which is now R1 plus R rotational plus 0.5 R2 prime. You got it? For that,
Yeah,
when we substitute here in the R no load relation, sorry, I got the wrong value here. لا مش 10 و2 من 10. So sorry, this is a, this is not right. This is the R no load. يعني in order to get R rotational, we need to use this relation. أنا ما خدتش بالي معلش. Sorry. Sorry, you are right, Hisham. Yeah, this is not the R no load. يعني R rotational should be 10.2 minus the other values we have. يعني we have R2 prime and R1, R2 prime. We obtain it here 2.7 and R1 2.9. So here 10.2 minus 2.7 plus 2.9. So this will be the value of R rotational. Okay. Thank you for your note. طيب. شباب, after obtaining the parameters, it's required here to determine the rotational loss. Already we obtained the rotational loss as we discussed. So rotational loss, and this is the relation, and it's already calculated here again. So B rotational equals طبعا you can obtain it as here he obtained it as no load losses minus I square multiplied by R1 plus R2 prime. Is it right, Shabab? Here
0.5 I think R2 prime.
You get it from here. لا ازاي 10.2 minus 2.7 plus 2.9. لا, it's higher than
No, 2.7 it should be 0.5 multiplied by, because as the first line of the equation.
Here this is divided by 2. Yeah, it's 0.5 R2 prime. So what is the value now of R rotational? 10.2 minus 2.9 minus 2.7 over 2. What will be the value? It's higher than
almost 6 ohms.
Around 6 ohms. So the rotational loss can be obtained now as I square, I no load square multiplied by the value of rotational loss here. And from the equivalent circuit at no load, we can say B equals I square multiplied by R1 plus 0.5 R2 prime plus P rotational, which is the 125 watt. This is the no load losses. So we can say now P rotational equals 125 minus I square multiplied by these values. Okay, so this is R1 and this is R2 prime over 2. So finally the rotational loss will be 72.94 watts. By the way, we consider rotational losses constant during the operation, whatever the loading condition. Why? Because it consists of two parts. One part is the mechanical loss due to friction, and we consume the friction loss constant because the change of the speed from no load to full speed will not be very high. So we assume constant friction loss. And the other part of rotational loss will be core losses. And core losses will be constant for the machine since the applied voltage is rated. It will not be changed if the voltage applied is constant. But it will be different if it will be vary if you change the applied voltage to the machine. So if you keep the machine working at rated volt, you can assume rotational loss to be constant all of time. Another example here for single phase induction motor, Shabab. It's related to previous problem. So for the previous problem, determine the input current, power factor, developed torque, output power, efficiency of the motor, air gap power, and rotor copper loss if the motor is running at rated speed when connected to 120 volt. So now the machine is connected to 120 volt. We have all of motor parameters, and we know the speed. Speed was given in the previous example, which is 1730 RPM, which means you can now obtain the value of slip. So firstly, Shabab, to solve such a problem, induction motor operation is dependent on the value of the slab of the motor. دايما slab dependent شباب. So we should firstly obtain the value of slab because all of the equivalent circuit and operation will depend on the value of slab. So we can say now NS. طبعا NS here it is 1800, which is the most close value to 1730. If even if the number of poles are not given in the example, okay. Once you know the value of speed, you can get the exact value of synchronous speed. So for 1730, the synchronous speed will be 1800. So you can obtain the value of slab. So this is our slab now. Now you need to substitute in the equation here or the values here in order to obtain the equivalent circuit in the simple form as Z forward and Z backward. So simply you can say Z forward equals RF plus JXF, which is nothing but the parallel combination of these two branches. So just multiply this branch impedance by that branch impedance over the summation of the two branches impedances. Okay, this will give you the effective or the equivalent impedance of these two parallel branches, and the same is also for the lower part. So this is the way to get ZF and ZB. After getting ZF and ZB, so this is Z forward and this is Z backward, we can substitute in the equations or the equivalent circuit of the machine. And even if you don't like to plot it here, but if you would like to plot, you can just add the impedance of stator, which is 2.9 J 3.26, and here you have Z forward and Z backward. Sorry, this line is not here. Okay, and Z backward. Okay, so this is the equivalent circuit now. After getting Z forward and Z backward, we can calculate the overall impedance of the motor, which is Z stator plus Z rotor. So it's nothing but the overall resistance plus the overall reactance. So this is now the motor impedance. You have the motor volt. So simply you can say current equal voltage over impedance. So this will be the value of current. And this angle represents what, Shabab, now? The
power factor.
Exactly. So we can say now power factor equal cosine of 51.61. So this will represent the motor power factor now. Okay, it's written here. This is our
lagging
power factor. طبعا all of time يا شباب the induction motor power factor will be lagging. صح يا شباب? All of time the induction motor power factor will be lagging. طبعا synchronous motor can be lagging or leading. It's up to the excitation value. Okay, but here because there is no excitation, the induction motor power factor all of time will be lagging power factor. So finally, after obtaining power factor, we can say now power input equals VI cosine theta. Okay, so we have V, we got I and the cosine theta, so we can obtain the input power. So the input power, Shabab, is 322.81 watts. Let's continue our analysis. We have the synchronous speed, which is NS multiplied by 2 pi over 60. This is now to convert the value of RPM to radian per second. So this is now representing omega s. And we have currents. So we can say now gap power equals I2 multiplied by R2 forward minus R backward over omega synchronous. So this will represent, Shabab, the amount of torque. Someone can say where is the value of slab? We used to use the equation P gap equals I square multiplied by R2 prime over S. This is for 3 phase. By multiplying by 3. But here we already included the S values with an RF and RB. So this part now representing the overall torque, ya shabab. Okay, this now representing the overall torque. However, if you would like to represent the overall power absorbed, you should say RF plus RB, not minus RB. We said this and discussed it in clearly last class. So This is now torque. Torque equals I square multiplied by RF minus RB over synchronous speed. So this is now the value of torque. طبعا this is considered as the electrical torque, developed torque, not the output shaft torque. So we still have friction. Mechanical power developed can be calculated as torque multiplied by omega multiplied by 1 minus s, and you already have the value of s. So simply you can obtain the mechanical power. Mechanical power, you know, it's equal to 1 minus s multiplied by B gap, and this is B gap effective, which will be affect the output. So we should consider the difference between B gap forward and B gap backward. So this is now, shabab, the value of B mechanical. And we have the rotational loss we already calculated before. So you can say now B mechanical minus B rotational equal the output power. So as you can see, shabab, this is now the output power. When you calculate the motor efficiency, can you see? Efficiency is 49%. Take care that the machine is working at rated, which means the efficiency should be very close to the maximum efficiency, by the way. Yani efficiency at rated speed or rated power of the machine will not be the maximum efficiency, but very close to maximum efficiency, which means maximum efficiency, shabab, can be 50 something, 52, 53, like that. Now, can you imagine the difference in efficiencies between three-phase and single-phase? What do you think, shabab? What is the reason behind that small efficiency?
You mean in three-phase?
Comparing three-phase with single-phase. Yani three-phase has higher efficiency compared to three-phase. Why?
Because the losses will be divided by 3.
Yani it's not only the matter of supplying the machine by 3 or single phase. Yani it's not because of that. But yani we have a main reason, okay? And we can justify it here from the equations. You have, firstly, for three-phase, you have high power. And for high power, you have very small resistance. And the copper loss will be very small. So this is for high power machines. And for small power machines, you have very thin conductors. And for that, the current is small and the value of resistance is high. So the copper loss will be high. This is one reason. Also, due to the performance or the operation of the single-phase induction motor, we said we have forward and backward power. And B gap effective, which will be converted to mechanical, equals B gap forward minus B gap backward. In three-phase, we don't have backward component to reduce the amount of gained power. So this is another reason here why we have less output power compared to three-phase. Yani in three-phase, the effective B gap equals the total B gap. However, here it's equal to the difference between forward and backward flux power. So this is one reason here why we have very small output power for single-phase motors. So this is one of the drawbacks of single-phase induction motors. It's small efficiency. Now, shabab, we need also to obtain the air gap powers due to forward and backward. So simply we can say I square R forward is power forward, and I square R backward is the power backward. And as you can see, this is the forward power and this is the backward power. If we are working in three-phase, the total power should be one of the only this value, okay? But it should be higher. It's not for one phase. But here, as you can see, because we have part of gap power in backward, so the resultant power will be the difference between them. Okay. Now, in order to calculate not the effective gap power, the gap power seen by the supply, it should be the summation of this power, because either backward or forward power are obtained from the supply. So in order to obtain the input power, you should summate both of them. شباب, this point is very important. You have to understand it very well. If you would like to obtain the effective gap power, which will affect the output power or mechanical power, you should get the difference between powers, as we made here in torque. Okay, in previous slide here, we get I square RF is nothing but B gap forward, and I square RB is nothing but B gap backward. So we could say T equal B gap forward minus B gap backward over omega. We didn't take the summation or adding the two values together. لا, we have to subtract the two values. Why? Because the effective value of gap power on the torque will be the difference between the two powers. Okay. However, in terms of supply, we need to calculate the total power from the side of the supply. So you should add the backward and forward power. So this is now considered as the two or the overall gap power. Now, regarding the rotor copper loss, طبعا simply for rotor copper loss, you can say it's equal to the value of power multiplied by S, B gap multiplied by S. So as you can see, B gap forward multiplied by S, this part representing the copper loss on the forward component, and this considered as the copper loss in the backward component, which is 2 minus S multiplied by B gap backward. So this is representing the forward copper loss of rotor, and this is representing the backward copper loss of rotor. The total copper loss for sure has to be the summation of the two powers. So this is now considered as the overall rotor copper loss. Now this was the last slide شباب in single phase induction motor. So in the single phase we could alhamdulillah cover the assigned materials. Okay, we understood the construction of the motor, the theory of the operation of single phase, the power flow of the and the two opposite rotating field, the double rotating field theory, methods of starting of single phase induction motor, and modeling and analysis of single phase induction motor. I wish that the topic of single phase induction motor be clear now, and you are welcome if you have any question. تفضلوا يا شباب. Any question يا شباب? Everything is clear الحمد لله.
Yes, alhamdulillah.
طيب الحمد لله رب العالمين. اوكي يا شباب, يلا see you ان شاء الله next class. السلام عليكم ورحمة الله.
دكتور
تفضل يا شباب.